Okay, so far we have studied various properties of groups, subgroups, normal subgroups, group homomorphisms, isomorphisms of groups, and so on. And we next want to study an important operation called quotients of groups. And in order to do that, I want to talk about cosets of a subgroup in a group. Before that, let me recall for you quickly the notion of an equivalence relation on a set, which many of you may have seen before, but this is very important for the course. So let me quickly define it and check its important properties, and then we will apply it to the case of a subgroup of a group. So review of equivalence relations. On a set. So let S be a set. Okay, so for this video we are only going to look at some sets, and there is no group here. So let S be a set. An equivalence relation on S is a relation okay, so it's a relation denoted by this symbol here. It's a relation among elements of S. So we say that two things are related, and we write this symbol. This means that A is related to B. So A is related to B is denoted by this symbol. So an equivalence relation is a relation on a set, which is to say it's a relation among elements of set of that set. So it's very precisely speaking, it's a subset of S cross S, but I don't want to get into this formal definition because it's confusing if you have not seen it before. So it's simply a relation, and when you see this, you think of a way of saying that two things are related, or it tells you if given two elements they are related or they are not related. But the relation must satisfy the following conditions. A must be related to A for every element of S. Okay, so an element must be related to itself. If A is related to B, then B is related to A. Okay, so this is true for every A, B in S. So the third property is called transitive property. If A is related to B, B is related to C, then A is related to C. So this is true for all A, B, C in S. Okay, an element must be related to itself. If an element is related to another, that element must be related to A. If an element is related to B, B is related to C, then A is related to C. Okay, the most important example, a trivial example really, is equality. Take for example on Z. Okay, so you say that A is related to A if A is equal to A. So equality is a basic example of an equivalence relation. Every element is equal to itself. If A equal to B, then B equal to A. If A equal to B, B equal to C, then A equal to C. So there is no surprise that equality is an equivalence relation, but there are more interesting equivalence relations, and hence you actually do talk about equivalence relations because there are equivalence relations that are not equalities. So another example, take again the integers, but now you say that, and so you say that A is related to B if A minus B is divisible by 4. Okay, so A is related to B if A minus B is divisible by 4. So this is my definition of a new equivalence relation. So this is the definition. For example, 5 is related to 5, of course, because 5 minus 5 is 0. So earlier equality was the only relation, but now we have more, because 5 is also related to 1, right? So 5 is related to 5 because 4 divides 5 minus 5, which is 0. But 5 is related to 1 because 4 divides 5 minus 1, which is 4. Similarly, 5 is related to 21, right? Or rather, 21, because 4 divides, what is 5 minus 21? That is minus 16, right? And 4 divides minus 16. So 5 is related to 25, 5 is related to 29, 5 is related to 34 or 33, and so on. So 5 is related to 5, but it's also related to a lot of other integers. But 5 is not related to, let me use that symbol, to 26. So 5 is not related to because what is 5 minus 26? 4 does not divide 5 minus 26, which is minus 21. So 5 does not divide that, 4 does not divide it. So 5 is not related to 26. So this is a more interesting example of an equivalence relation than equality. So because we are doing group theory, let me define another equivalence relation which is more appropriate for us and more important for us. So let G be a group and let H be a subgroup of G. So I have a group and a subgroup of that group. So I define A is related to B. So let me start like this. Let A and B be two elements of G. We define that A is related to B if let's say A inverse B is in H. So actually I forget something here. Before I continue with the third example, I just wrote something. I never said that it is an equivalence relation. I should prove it, right? So that I will not check. I'll quickly say why it should be true. See, if the equivalence relation in the second example is that A is related to B if 4 divides A minus B. So certainly, so why is this an equivalence relation? So certainly A is related to A. That's okay, because A minus A is 0 and 4 divides it. If A is related to B, then B is related to A, because if A is related to B, 4 divides A minus B. But then 4 divides B minus A also. So B is related to A. If A divides B and B divides C, that means 4 divides A minus B and 4 divides B minus C. But if 4 divides A minus B and B minus C, 4 divides their sum, which is A minus C. So this implies 4 divides A minus C, so A is related to C. So we have checked all the three properties. So this is an equivalence relation. Now let's check that this is an equivalence relation. What are we saying? Let H be a subgroup of G. Two things are equivalent if this element constructed from them is in the group H. This is an equivalence relation. Why? First of all, is A related to A? Yes, because you have to ask yourself whether A inverse A is in H. It is in H because that's just E. Okay, so that's okay. If A is related to B, that means A inverse B is in H. Alright, by definition. But because H is a subgroup, A inverse B whole inverse is in H. Anything in H contains its inverse also. H contains its inverse also. So A inverse B is in H means A inverse B whole inverse is in H. What is A inverse B whole inverse? That is B times B inverse times A. Right, this we have seen before. A inverse times B whole inverse is B inverse times A inverse inverse, but that is nothing but B inverse A. So if B inverse is in A, this is the meaning of B being related to A. Remember, A is related to B. If A inverse times B is in H, B inverse times A is in H means B is related to A. So the second property holds. Now let's take A is related to B, B is related to C. That means A inverse B is in H and B inverse C is in H. Right? A inverse B is in H, B inverse C is in H. This means because H is a group, subgroup, it is closed under multiplication. So if A inverse B is in H, B inverse C is in H, the product is in H. So A inverse B times B inverse C is in H, but that means A inverse C is in H because that is the product. That means A is related to C. So this is an important equivalence relation this is an equivalence relation, and this is something that we will explore in great detail later. So I looked at 3 equivalence relations on sets. So now some important properties of equivalence relations. Equivalence relations give equivalence classes. So what do I mean? So let's say S is an arbitrary set. I am going back to the setting of general setting of a set and an equivalence relation on that set. So now for A in S, define the equivalence class of A. The equivalence class of A, as we denote it by this symbol. Okay, so let's say the equivalence class of A is denoted by A in square brackets. This is all elements in S such that A is related to B. Okay, so this is very simple. The equivalence class of A is the collection of elements that are equivalent to B. So in our examples, what is the equivalence? In the first example, where the equality is the equivalence relation, equivalence class is very simple, right? In the first example, equivalence class A is equivalent to B if A equal to B. In this case, the equivalence class is all elements which are equivalent to B, equivalent to A, but this means, so this is B in Z such that B is equivalent to A, but this is same as B in Z, B is equal to A, so that is just nothing but A, right? So in this case, the equivalence class is just the set. In the second example, we have defined A, here S is Z, A is equivalent to B if 4 divides A minus B. Okay, so I'm going to first write down the equivalence class of a specific element for so that you see what is going on. So let's say 5 that we have seen earlier. What is the equivalence class of 5? So these are all integers such that B is such that 5 is equivalent to B. This is same as writing B is equivalent to 5 because this equivalence relation has that property, right? So this is all integers such that they are equivalent to 5. So this is all integers such that 4 divides 5 minus B. So if you write these down, what would they be? Just write like some of them. So 0 is not an element in this because 5 minus 0 is 5. 4 doesn't divide it. So 1 is there. 5 minus 1 is divisible by 4. So 1 is an element of the equivalence class. The previous element would be minus 3. Right? Because minus 3 is related to 5 because 5 minus minus 3 is 5 plus 3, 8. It is divisible by 4. Similarly, next will be 5, 9, 13, 17, 21, 25, 29. You see the pattern here, right? These are all, the previous element will be minus 7. You can see that they are all integers and they starting with 1, you keep increasing by 4 and keep decreasing by 4. We have used the notation 4z. Remember 4z was all integers which are multiples of 4. So this is minus 8, minus 4, 0, 4, 8 and so on. Right? This is similar to that, right? It's not quite that, of course it's not that, but it looks like 0 is replaced by 1, 4 is replaced by 5, 8 is replaced by 9, minus 4 is replaced by minus 3. So I can write this as 4z plus 1. So you take 4z and add 1 to each element, right? So add 1 to each element. So this is 4z plus 1. So the equivalence class of 5 is just 4z plus 1. Okay, we will come back to this and discuss this in more detail. But the thing to keep in mind now is 4z, the equivalence class of 5. The equivalence class of 5 is 4z plus 1. I will let you do this as an exercise. What is the equivalence class of 6 is 4z plus 2. For 7 it will be 4z plus 3. For what about for 8? You will see that it is exactly equal to 4z. So, and for 9 it will be 4z plus 1 again, and for 10 it will be 4z plus 2. So they keep coming back, right? It's periodic in that sense. So as I said, we'll come back to this example and study it in more detail later. In the third example, the set was a group G. Fix a subgroup H. And the relation was A is related to B if...
Sir, there's no battery.
Okay.
We'll continue in Camtasia.
Okay.
Right. At last, when you're finishing, we'll
okay.
capture the Camtasia.
Sure.
Then I can sync off.
Okay.
Send it.
So this part there will be no video, but that's okay.
Yes, sir. You carry on, sir.
Okay. So recall that in this example, we have declared that A is equivalent to B if A inverse B is in H. Right? So that was the example. We saw that A inverse B in H, then A is related to B, that's an equivalence relation. What are the equivalence classes of... so now let A be in G. What is the equivalence class of this? So this is all elements B in G such that A is related to B. By definition, this is the equivalence relation, equivalence class, right? But this is all B in G such that A inverse B is in H, right? This means all B in G such that A inverse B equals some H. It's an element of capital H, so I'm going to give it a name, small h. So this is same as all B is in capital G such that B is AH, where H is in G, H, right? So it is all elements of capital G which can be written as A times small h for some suitable small h in capital H. This is nothing but, then I can eliminate B from this whole description. It is AH where H is in H. So is this clear? All the equalities here. Originally these are all elements B equivalent to A. That means A inverse B is in H. That means A inverse B is equal to some small h, which is equivalent to, if A inverse B equals H, then B is AH, right? This is if and only if. So I'm going to rewrite this as B equals AH. But then I eliminate B from the description completely. So this is all AH where H belongs to H. There is another notation for this. So this is the definition. So define AH to be. This is very similar to the way that we define subgroups of Z. So I take the subset obtained by multiplying every element of capital H by small a. So the equivalence class of A in this case is just AH. So now I want to define a proposition which is prove a proposition which is very important for us. Let S be a set and let this be an equivalence relation on S. Then the equivalence classes of elements of S partition S. So partition S, that is they are all S is a disjoint union of okay. So what happens is, I will prove this in a minute, but what happens is that you start with a set S, you have an equivalence relation on this set. Then if you take equivalence classes, they may coincide but there will not be intersections for two distinct cosets. So these are all equivalence classes. Okay, so they partition the set. So they partition the set, meaning every element in the set is in one of the equivalence classes and there is no common element between two distinct equivalence classes. So this is the proposition. So let's prove this. So first of all, if A belongs to S, then A belongs to A, right? This is because, remember, one of the first property of an equivalence relation is that an element is related to itself. So this equivalence class, remember, equivalence class of an element is all elements in the set S such that B is related to A. So A is related to A, so A is in the equivalence class of A. So certainly S is a union of equivalence classes. correct? If you take all equivalence classes and you take their union, you get S, because every element of S is in an equivalence class. Certainly equivalence classes are all subsets of S. So this is fine. Now on the other hand, I claim that if equivalence class of A and equivalence class of another element B are not disjoint. Remember, disjoint means they have no common elements. If they have not disjoint, then they are equal. So what I'm saying is that if you take the equivalence class of A and equivalence class of B, if they have something in common, they must be equal. So in fact they must be equal. So they can't have some things in common but be distinct. What is the proof of this? So remember, these are not disjoint, meaning there is some common element. So let's say C is in the intersection of B. See, all of this is happening within S. So this and this are subsets of S, and they have something in common. So C is in both of the equivalence classes. That means A is related to C and B is related to C, right? Because C is in A, so A is related to C. C is in B, so B is related to C. This implies that A is related to B. Because A is related to C, C is related to B. So by the third property of an equivalence relation, A is related to B. That means A is in B, right? So, and B is in A. So A is in the equivalence class of B, B is in the equivalence class of A. So that means, because if any element, if some other element D is equivalent to A, then it's equivalent to B also. So it's in B. If it's equivalent to B, it's equivalent to A also. So this is fine. So this proves that if two equivalence classes are not disjoint, then they are equal. They are exactly identical. So this proves the claim. Now it follows that S is a disjoint union of equivalence classes, because we have either two equivalence classes are disjoint or they are identical. So because of what we have shown, if they have some elements in common, they are identical. That's what we have shown here, right? If A and B are not disjoint, in other words, they have something in common, they are identical. So if you have two equivalence classes that have some elements in common, they are identical. So if you take distinct, now take distinct, so not equal equivalence classes. They are all mutually disjoint because they are distinct, right? They are not equal. They are not equal, so they are distinct. Hence, any two of them being distinct are disjoint, and their union is because every element, remember, of S is in a equivalence class. So you take that equivalence class, and that is one of the distinct equivalence classes that we took earlier. So distinct equivalence classes partition S. This proves the proposition. No need to say really distinct, because if they are same, we don't need to repeatedly take it, right? So these are equivalence classes. Partition S is the statement of the proposition, and I have proved it. And I will work this out in the first two examples and leave the third example for the next video.
Already finished also.
In 2 minutes.
Okay, sir.
Not, no.
When you are going to conclude, just tell me. I'll.
Yeah, so one moment. So in the first example, in example 1, remember where S was Z and A is related to B if A equal to B. What are the equivalence classes here? Equivalence classes are just singleton sets A. Equivalence class of A is just the set A. So, and Z is a union of certainly it's a union of singleton sets. In example 2, S was again Z and A was related to B if 4 divides A minus B. Here there are exactly 4 equivalence classes. So namely the equivalence class of 0, which is 4Z, the equivalence class of 1, which is 4Z plus 1, equivalence class of 2, which is 4Z plus 2, and equivalence class of 3, which is 4Z plus 3. Okay, and if you go back and see the examples, the equivalence class of 5 was actually just 4Z plus 1, which is same as the equivalence class of 1. 6 is 4Z plus 2, 7 is 4Z plus 3, 8 is 4Z. So you get nothing new by considering other integers. So Z is the disjoint union of 4Z. The symbol for disjoint union is this, 4Z plus 1, disjoint union 4Z plus 2, 4Z plus 3. It's clear that any integer is in one of them, because all you need to check is divide by 4 and see what the remainder is. If the remainder is 0, it's here. If the remainder is 1, it's here. If the remainder is 2, it's here. If the remainder is 3, it's here. And they certainly have nothing in common. 4Z plus 1 and 4Z plus 2 cannot have any element in common. So these are the different partitions for that partition equivalence class. I'm going to stop the video here. We have still to discuss the equivalence classes of the relation given by a subgroup of a group. That we will do in the next video. But to recall what we have done in this video, we have talked about equivalence classes on arbitrary sets. We looked at some examples, and I proved a proposition saying that equivalence classes of an equivalence relation on a set partition that set, and which is very important for us in the context of group theory, because it will allow us to define cosets of a group, subgroup, and talk about quotient groups later on. So I'll stop the video here and continue with cosets next video. Thank you.